Dear students, today we will continue our discussions on chapter number 4, sections 4.7 to 4.9, that is motion in a plane with constant acceleration and relative velocity in 2 dimensions. I welcome you for this lecture session. Please note down all the important points. Wherever you feel that I am going fast, you can pause the video and note down the points. Physical quantities like position vector, displacement, average velocity, and instantaneous velocity are described using vector diagrams. In the figure A, the position vector r of a particle P in xy plane with O as origin is given by r is equal to xi plus yj. Please see the figure. Here O is the origin, P is the particle. So the line joining O and P, OP, is represented by a position vector r and its coordinates are xi and yj. Hence r is equal to xi plus yj. The displacement vector is shown in figure B, and in this case the particle has moved from point P to point P dash. The coordinates of P dash are x dash y dash. So then the displacement delta r is the distance between P and P dash, that is given by the difference of position vectors r dash and r. That is delta r is equal to r dash minus r, which is directed, delta r is directed from P to P dash. In component form, delta r is written as x dash I plus y dash j minus xi plus yj. That is equal to I into delta x plus delta y. Delta x is a displacement in x direction and delta y is the displacement in the y direction, and this is also shown in the displacement diagram B. Velocity. Velocity can be explained using the vector diagrams. First, let us take up average velocity. Average velocity is the ratio. This is defined as the ratio of displacement and corresponding time interval. Therefore, it is average velocity is represented by V bar average. V bar average equals displacement delta r divided by the time interval delta t. That is equal to delta xi plus delta yj divided by delta t. And this can be, numerator can be split as delta x by delta t plus delta y by delta t, and it is written as I into delta x by delta t plus j into delta y by delta t. Therefore, but we know that delta x by delta t is the average velocity in x direction plus average velocity in y direction is delta y by delta t. Therefore, V average or V average bar is written as equals Vx average I plus V y average into j. The direction of average velocity is same as that of delta r. The instantaneous velocity v vector v is defined as the limit of delta t tending to 0 of average velocity. So we can write instantaneous velocity v vector v as equals limit of delta t tending to 0 of delta r by delta t. So delta r by delta t we had defined earlier as the average velocity. So limit of delta t tending to 0 of ratio of average velocity is the instantaneous velocity, and it is written as dr by dt, that is differential of displacement r. As the delta t tends to 0, the average velocity approaches instantaneous velocity. Hence, delta t tending to 0, average velocity approaches instantaneous velocity. The direction of V average is parallel to the tangent to the path and is the direction of motion. This is explained using diagrams C, D, E and F. So wherein the particle has moved from position point P to P1 in figure C and point P to P2 in figure D and P to P3 in figure E. That is at different instantaneous of time T1, T2 and T3 respectively. Here the displacement vector is represented by delta R1, delta R2 and delta R3. And finally, when delta t tends to 0, the the average velocity becomes the limit of delta t tending to 0 of delta r by delta t becomes instantaneous velocity, and it is dr by dt, and this is shown in figure F. Therefore, the instantaneous velocity in component form is written as vector v is equal to dr by dt. There, that is also as defined as the limit of delta t tending to 0 of I into delta x by delta t plus j into delta y by delta t. That is, so vector v instantaneous velocity is equal to I into dx by dt plus j into dy by dt. That is equal to vxi plus vyj, where vx is the instantaneous velocity in x direction plus vy, where vy is the instantaneous velocity in y direction. Therefore, magnitude of vector v instantaneous velocity is written as v is equal to square root of vx square plus vy square. Please see the diagram at G, where the components of vector v are split into vy and vx. Vx is the velocity, average instantaneous velocity along the x direction, and vy is the velocity in the vertical direction, that is y direction. And there is the angle between the velocity vector v and the horizontal is theta. So theta can be found by using the Pythagoras theorem, that is, the direction of instantaneous velocity is given by tan theta is equal to Vy by Vx, where Vy is the opposite side and Vx is the adjacent side. Therefore, theta will be equal to tan inverse of Vy by Vx. Therefore, Vx, Vy and theta are shown in figure G. The theory of acceleration in two dimensions, that is in a plane, can also be explained using vector diagrams. We know the average acceleration is defined as the ratio of change in velocity to the time interval. Therefore, the average acceleration represented by A suffix average is equal to delta V by delta T, where delta V is the change in velocity and delta T is the time interval. That V can be split into delta Vx divided by delta T into I plus delta Vy divided by delta T into J. That is, the average velocity is split into two components. That is, velocity along x-axis Vx and velocity along y-axis Vy. That also is again the change in velocity to ratio is the acceleration. Therefore, that can be V average acceleration can be written as ax into I plus ay into j, where ax is the acceleration in x direction and ay is the acceleration in y direction. The average acceleration for three time intervals delta t1, delta t2 and t3 are shown in the figures A, B and C respectively. Here the the particle has moved from P to P1 in figure A, and its acceleration, direction of the acceleration also has changed from V to V dash, whereas in figure B the position is at point P2 and its velocity is V dash and the direction is perpendicular to the velocity. Here you see the diagram, it is perpendicular to the velocity. Similarly, in P3, the velocity has changed from V to V dash and its direction of acceleration is also changed. So, delta V is also shown in the figure. Hence, in the limit delta T tending to 0, the average acceleration is as shown in figure D. See here, the average velocity is the line shown here represented by V, and perpendicular to V is the direction of acceleration. Please note it very carefully. Also note that in one dimension the velocity and acceleration of an object are always along the same straight line, that is either in the same direction or in the opposite direction. However, for motion in 2 or 3 dimensions, the velocity and acceleration may have any angle between 0 degrees and 180 degrees between them. Motion in a plane with constant acceleration. Velocity of a particle V moving with a constant acceleration A at any point t is given by the equation vector V is equal to vector V naught plus at, where V naught is the velocity at time t equal to 0. This is a basic equation. Sometimes we write V is equal to u plus at, where instead of V naught we write u. So some books refer it as u, vector u, initial velocity vector u. Here we have written V naught. Therefore, average velocity over the time interval t is given by the relation V average. So, initial velocity plus final velocity divided by 2, average of the two velocities. In terms of components, Vx is equal to, so in the x direction, x-axis, we have split the velocity into axis, x-axis in x direction and y direction. Therefore, Vx is equal to, using this equation, V naught x plus axt. And similarly, in the y direction, Vy is equal to V naught y plus ayt. Displacement. Now, displacement of a particle. Therefore, displacement we know the final position vector minus initial, that is r, vector r minus vector r naught, that is equal to r is v plus v naught by 2 into t, that is equal to v naught plus at plus v naught. So we have substituted for V. V is equal to V naught plus AT, and this V naught divided by 2 into T. Therefore, R is equal to, moving R naught to the right direction, we get R naught plus V naught T plus AT square. Simplifying, we get this relation. In terms of components, X is equal to, that is the displacement X is equal to X naught plus Vx naught T plus Ax T square, and Y is equal to Y naught plus vector V of Y naught T plus half AT square. That is, we are writing this equation, this relationship in terms of X and Y components. Motion in plane can be treated as two separate simultaneous one-dimensional motion. So, while treating motion in a plane, we have to treat the one-dimensional motion separately with constant acceleration along two perpendicular directions. The two perpendicular directions are x-axis and y-axis. Next section is 4.9, relative velocity in two dimensions. The concept of relative velocity was introduced in chapter number 3 for motion along a straight line. This can also be extended to include motion in a plane, that is two-dimensional, or in three dimensions, that is in space. Suppose that two objects A and B are moving with velocities vector v, Va plus vector Vb, each with respect to some common frame reference. Usually ground is taken as a reference point. So Va is with respect to the ground and Vb is also with respect to the ground. The velocity of the object A relative to that of B is given by the relation vector AB. That is, velocity of A with respect to B equals VA. VA is with respect to ground minus VB. VB is also with respect to ground. And similarly, velocity of B with respect to A is, that is, earlier it was A to B, now it is B to A. It can be written as vector VBA is equal to vector B minus vector VA. That is, velocity of B with respect to A is equal to velocity of B minus velocity of A. Therefore, VAB is equal to minus of VBA. That is reverse, negative. And modulus of mod vector VBA is equal to mod of vector VAB. Worked examples for section motion in a plane. Question number 3. A motorboat is racing towards north at 25 kilometers per hour, and the water current in that region is 10 kilometers per hour in the direction of 60 degrees east of south. Find the resultant velocity of the boat. Let us solve it. Please see the figure. First, in all such cases, we have to mark the directions north, south, east, west as shown in the figure. Here, Vb is the speed of the boat or velocity of the boat, which is moving towards north as given in the question. And similarly, the water current is at an angle of 60 degrees east of south. East of south means this is the angle. This is 60 degrees, and the resultant of these two vectors VB and VC is found by completing the parallelogram as shown in the figure. That is, from here VB R and this east and this parallelogram, and OR is the resultant. So this is the R is given by the equation square root of VB square plus VC square plus 2VC VB into cos of 180 minus 60 degrees. Please note that the angle theta is east of south, that is 60 degrees. If you take the total angle in the first quadrant, it becomes 180 minus 60, that is equal to 120 degrees. Therefore, substituting the values of VB and VC, we get R is equal to 25 square plus 10 square plus 2 into 10 into 25 into the cos of 180 minus 60, that is cos 120 is minus half. From tables you can refer it, that is equal to 22 kilometers per hour. Now we have to apply law of sines for finding the direction, that is r by sine theta equals Vc by sine phi. Therefore, sine phi is equal to Vc by r into sine theta. Therefore, that is equal to 10 divided by 22 into sine 120. So that is equal to root 3 by 2 into 22, and its value is 0.397. Next question. The position of a particle is given by the vector r is equal to 3t into I plus 2t square j plus 5k, where I, j and k are unit vectors, where t is in seconds and coefficients have the proper units for r to be in meter. So part A is find Vt and At, that is velocity at time t and acceleration at time t of the particle, and B, find the magnitude and direction of Vt at t is equal to t seconds. So there are two parts. Let us solve the part A. That is, we know that the velocity in a motion in a two plane is defined by dr by dt. So dr, r is given as 3ti plus 2t square j plus 5k. Put the value of r. So differentiate. We have to find the differential. To solve this problem, you should know the differentiation. So therefore, d by dt of 3ti is 3i plus d by dt of 2t square is 2 into 2t into j, and d by dt of 5k is 0. Therefore, velocity vector v is equal to 3i plus 4j, 4t into j, as shown in figure. Let it be equation 1. Therefore, the acceleration is a equals dv by dt. By definition, acceleration is change in velocity to change in time. Therefore, that is equal to d by dt of v is 3i plus 4tj. Therefore, that is equal to 3i plus 4tj. Therefore, a is equal to d by dt of 3i is 0. And again plus d by dt of 4t is 4j. Therefore, acceleration a is equal to 4j, that is 4 meters per second along y-axis. Now we have to find the velocity at t is equal to 1 second. That is, in part B, the question is we have to find the magnitude and direction of Vt at t equals 1 second. Therefore, V we have found as V is equal to 3i plus 4tj. Therefore, put the value of t as 1 second. Therefore, V will be equal to 3i plus 4 into 1 second. That will become 3i plus 4j. Therefore, magnitude of velocity vector v equals square root of 3 square plus 4 square. That is equal to 3 square is 9, 4 square is 16. 16 plus 9 is 25. Square root of 25 is 5 meters per second. And the direction theta can be found by direction theta is equal to tan inverse of opposite side by adjacent side. Tan inverse of Vy by Vx. That is equal to Vy is 4 here. Vy is 4 and Vx is 3. That is equal to tan inverse of 4 by 3. From tables you will find that it is 53 degrees with x-axis. Therefore, A is equal to 4 meters per second. Motion with constant acceleration. We will solve an worked example on this. A particle starts from origin at t equal to 0 with a velocity of 5 meters per second and moves in xy plane under the action of a force which produces a constant acceleration of 3I plus 2j meters per second square. Part A. What is the y coordinate of the particle at the instant of its x coordinate if the x coordinate is 84 meters? Part B is what is the speed of particle at this time? Given, it is given, we will write down the given. Velocity V naught is equal to 5I meters per second and acceleration is given as 3I plus 2j. Therefore, applying the formula R is equal to R naught plus V naught t plus half AT square. That is S is equal to UT plus half AT square formula. So R naught is 0 here because it starts from origin. Therefore, R is given by V naught t plus half AT square. Substituting the given values of V naught and A, we get 5 times R is equal to 5ti plus half 3I plus 2j into t square. Therefore, R rearranging the coefficients of I, we get R is equal to 5t plus 3 by 2 t square into I plus t square. Therefore, x of t is 5t plus 3 by 2 t square plus yt is t square because the coefficient of j is t square and coefficient of I is x. Therefore, we will put the values at x at 84. X is equal to 84. Therefore, t is equal to what? We have to find. Therefore, xt is 84 equals 5t plus 1.5 t square. Let it be equation 2. Solving, we here to solve the equation 2, simultaneous equation and find the value of t using the standard formula. We get the value of t as 6 seconds. You have to solve this equation. Please do it yourself. Therefore, y will be equal to t square. That is, t square is y of at x is equal to 84 is 6 square. That is equal to 36 meters. Let it be equation 3. Then we will solve the part B to find the speed of particle at this time. From equation 1, we know R is equal to 5t plus 3 by 2 t square into I plus t square j. So we have to find the velocity. Velocity is differential of displacement, that is dr by dt, that is equal to V is equal to dr by dt is 5 into 5 plus 3t I plus 2 times t into j. That is differential of R. That is 5 plus 3t plus I into I plus 2j. That is differential of this equation. Therefore, at t is equal to 6 seconds, put the value of t as 6 seconds in this equation number 4. We get V is equal to 5 plus 18, that is 23I plus 12j. Therefore, speed of v is given by modulus of v is equal to 23 square, that is x square plus y square, square root of 23 square plus 12 square, that is equal to 26 meters per second. Next, we will solve an example from relative velocity in 2 dimensions. Question number 6. Rain is falling vertically with a speed of 35 meters per second. A woman rides a bicycle with a speed of 12 meters per second in east to west direction. What is the direction in which she should hold her umbrella? So please see the diagram here. Let VB be the velocity of bicycle which woman is riding, and it is given that it is from east to west, that is east to west is this direction, east to west, and rain is falling vertically down. So let VR be the vector representing velocity of the rain. So we have to find the resultant of these two. Since it is a problem of the relative velocity, we have to find the difference between VB and VR. Therefore, velocity of the rain relative to the velocity of bicycle is VRB is equal to VR minus VB. So to find the minus VB, we have to reverse this vector. Therefore, it is given by the relative velocity vector, that is difference between VB and VR makes an angle theta with the vertical. It is given by the relation opposite side, VB by VR, that is equal to 12 by 34, that is equal to 0.343. That is from table. We have to find the value of theta by taking tan inverse. So theta is equal to tan inverse of 0.343, that is equal to 19 degrees. So now we will again briefly summarize motion in a plane, symbols, dimensions and unit. Position vector is r and its dimension is L within brackets, and unit is meter and it is a vector. Displacement is delta r, that is change in the position is delta r, its dimension is L and unit is meter. Velocity is average velocity is v bar and its dimension is Lt to the power of 1, that is distance over time. So meters per second, it is written as delta r by delta t. Instantaneous velocity vector v is equal to dr by dt, and acceleration, average acceleration symbol is a bar, Lt to the dimension Lt to the power of minus 2 meters per second, that is del v by del t, and instantaneous acceleration is vector a, that is equal to dv by dt. With this, I have concluded my lecture on motion in a plane and relative velocity in 2 dimensions. In the next chapter, we will take up projectile motion and uniform circular motion. Till then, goodbye.